Welcome to the deep dive. Look around you for a moment. I mean, really look, whether it's the seasons changing, maybe a seed turning into a plant, or even just, you know, what's happening when you cook dinner. Our world is just constantly shifting, isn't it? But what if there's a kind of hidden language behind all that change? Today, we're taking a deep dive into two really fundamental types of transformations, physical and chemical changes. Our goal here is to, well, cut through the complexity, get to the core ideas, and give you that foundational understanding so you can kind of quickly grasp the why behind things you see every single day. We're going to differentiate these changes, look at why they happen, and maybe uncover some surprising examples that might make you see your surroundings a little differently. Get ready to understand the makeovers happening all around us. Okay, so let's unpack this. Before we really zero in on physical versus chemical, it's kind of wild how many different ways we can even categorize change itself.
Oh, absolutely. It's not just one simple thing. I mean, the sources point out we can think about speed, right? You've got slow changes like mountains wearing down over ages versus fast changes like lightning or, you know, burning paper.
Right, instantaneous almost.
Exactly. Or think about periodic changes, things that repeat predictably, like the seasons or the moon phases, compared to non-periodic stuff, totally unpredictable things like earthquakes or, I don't know, catching a cold.
And then there's the desirable versus undesirable angle, like cooking food is good, we want that. Spoiled food, not so much.
Definitely. But what's really interesting there, and maybe a bit tricky, is how context flips that desirability switch.
How so?
Well, take cutting down trees. You might need the wood, so that's desirable for you, but for the environment, maybe not so great. Or rain, fantastic for crops if it's timely, but a massive flood, that's suddenly very undesirable. So good or bad change really depends on your perspective, doesn't it?
That's a great point. So we have all these ways of looking at change, but when we dig down into what's actually happening to the substance itself, the material, that leads us to these two big categories, right? Physical and chemical. And this is where it gets really, really interesting, I think. Let's kick off with physical changes. You can sort of think of these as, well, transformations where something might look different, maybe feel different, but deep down, it's still the same basic stuff.
That's a perfect way to put it. A physical change is essentially temporary. No new substance gets made. The actual chemical identity, the molecules making it up, stay the same.
Okay.
All the changes are the physical properties, maybe the state, like solid, liquid, gas, or its shape, size, maybe even color sometimes. But the key is the substance itself hasn't changed its core identity. And often, not always, but often you can reverse these changes.
So the classic example everyone learns.
Water. Has to be water, right? Ice melting into liquid water, water boiling off into steam, steam condensing back into water. Through all of that, it's just H2O.
Still water.
Still water. The molecules are maybe moving faster or slower, closer together or farther apart, but they're still H2O molecules.
And you bump into this all the time, probably without thinking, like tearing a piece of paper. It's still paper, just in bits.
Exactly.
Or dissolving sugar in your tea, it disappears, kind of, but the sugar's still in there, isn't it? You could get it back if you boiled off the water.
Precisely. It's just dispersed. That's a physical change. And even slightly weirder stuff like sublimation. You know, dry ice, solid carbon dioxide going straight to gas.
Yeah, skipping the liquid part.
Right, or those little naphthalene balls people used to use. Solid straight to gas.
Yeah.
It's still chemically the same stuff, just changing its state dramatically. But this brings up a good point, actually. Can all physical changes be reversed? We often think they can, but take chopping vegetables. If you chop a carrot into little pieces,
Okay.
each piece is still carrot, right? Same taste, same color, same stuff chemically, but, well, you can't really stick them back together to get the original whole carrot perfectly.
Ah, right. No unchopping the carrot.
Exactly. So that's a physical change. The carrot's nature hasn't changed, but it's practically irreversible.
That's a really important distinction. So physical changes are mostly about form, state, appearance, but the underlying identity is untouched. What happens when that identity does change? When it becomes something totally new?
Ah, now you're talking chemical changes. This is the real transformation. A permanent change where the starting materials, the reactants, are used up, and entirely new substances, the products, are formed. These new substances have completely different chemical makeups and properties.
So it's not just a disguise, it's a fundamental rewrite of what the substance is.
Precisely. An identity swap at the molecular level. And these changes are generally irreversible. You can't easily go back. Plus, they always involve energy changing hands, either releasing energy like heat or light or absorbing it.
Cooking feels like the prime example again here, doesn't it? Once you've cooked that egg, there's no going back to a raw egg.
Absolutely not. The heat causes the proteins to denature, to change their structure completely. New substances are formed. Or think about burning wood in a fireplace.
Right.
You get ash, smoke, heat, light. You definitely can't turn that ash back into a log. The wood molecules, the cellulose, have reacted with oxygen and broken down into carbon dioxide, water vapor, and other thing. Totally new stuff.
And rust. That reddish-brown stuff on old iron.
Classic chemical change. Iron reacts with oxygen and moisture in the air to form iron oxide rust. Rust is brittle. It's not magnetic like iron. It's a completely different compound. You can't just wipe the rust off and have the original iron back underneath in the same way.
Okay.
Even something simple like milk turning into yogurt or curd. That souring process, it's bacteria causing chemical changes, creating lactic acid, new taste, new texture, irreversible. And, think biologically, respiration, digestion. Those are incredibly complex series of chemical changes happening inside us constantly.
Wow. Okay, so if these are happening all around, how can you spot one? Are there telltale signs?
Yeah, there usually are. Look for a few key indicators. A change in color is often a big clue, like fruit ripening or metal tarnishing. The evolution of a gas, you might see bubbles forming. Like if you drop zinc into acid, it fizzes away, releasing hydrogen gas. Sometimes you can even test that gas, like with hydrogen's little pop sound of the flame.
Right, I remember that from school.
Exactly. And maybe the most fundamental sign is a change in energy. Does the reaction get hot? That's energy being released, like when quicklime dissolves in water. Or does it get cold? That means it's absorbing heat from its surroundings. Sometimes light or sound is produced too.
So look for color changes, bubbles, heat, light. Basically signs that something fundamentally new is being created or energy is being exchanged in a noticeable way.
You got it. Those are your big clues that a chemical reaction, a chemical change is likely underway.
Yeah.
But here's where it gets even more layered. Sometimes these two types of changes, physical and chemical, they happen at the same time.
Oh, okay. They're not always separate events. Give us an example.
The perfect everyday example is a burning candle. Think about what's happening there.
Okay, wax melts.
Right. The solid wax near the flame gets hot and melts into liquid wax. That's a change of state, solid to liquid. If some of that liquid wax drips down the side and hardens again.
Liquid back to solid.
Yep, that melting and solidifying, that's a physical change. The wax is still wax, chemically speaking, just in a different form.
Okay, makes sense. But the candle's burning down, it's disappearing.
Exactly. Because at the same time, some of that liquid wax is drawn up the wick by capillary action. It gets hot enough to vaporize, turn into a gas, and then that wax vapor burns in the flame. That burning reacting with oxygen.
Ah, that's the chemical change.
That's the chemical change. The wax molecules are breaking apart and reacting to form totally new substances, mainly carbon dioxide, gas, and water vapor, plus soot, maybe. That's why the candle gets smaller. It's the wax being chemically transformed and released as gases.
Wow. So one simple burning candle shows both things happening side by side. Melting is physical, burning is chemical. That really clarifies it. So, okay, we've distinguished physical and chemical changes. Why does this actually matter to, us listening right now, beyond just being interesting science?
Well, if you think of the big picture, understanding this difference is just fundamental. It touches almost everything. In daily life, it's why we cook food. The chemical changes make it digestible, safer, tastier. It's how our bodies work, breaking down food chemically to get energy.
Right, basic survival.
Totally. And then think about industry. Making anything new, soaps, detergents, plastics, paints, fertilizers, life-saving medicines, that all relies on controlling specific chemical changes.
Yeah, you need to create new substances with the right properties.
Precisely. And extracting useful things like getting iron metal from iron ore or aluminum from bauxite. Those are huge chemical processes. Even generating energy like burning fuel in power plants or cars is all about harnessing the energy released during chemical changes.
And physical changes matter too, right, for separating things.
Absolutely. Things like distillation to separate liquids based on boiling points or filtration or even just sorting materials, those rely on differences in physical properties. It's essential for refining materials and purification.
So it's not just abstract science, it's literally the foundation of how we make things, get energy, and even how life itself functions.
It really is. Understanding these two basic types of change gives you a lens to see the how and why behind so much of the world.
It's like having a shortcut to understanding the mechanics of, well, everything. Okay, so let's quickly recap this deep dive. We've got physical changes, temporary shifts, maybe in state or shape, but the substance itself, its chemical identity, stays the same. Think melting ice.
Right.
And then chemical changes. These are permanent transformations. New substances are formed with totally different properties, usually involving energy changes, and they're generally irreversible. Think burning wood.
Exactly. Costume change versus complete identity swap.
Perfect. Now that you've explored this, hopefully you'll start noticing these changes everywhere. Boiling water, rusting metal, baking a cake, leaves changing color. It might just click in a new way, a real aha moment about how your environment works.
So maybe the next time you see something change, just take a second and ask, is this just a physical rearrangement, like shuffling furniture? Or is it a chemical reaction, building something entirely new? What does that tell you about the constant dynamic transformations happening all around us, from the smallest scale to the largest?
A great thought to leave us with. Thanks for diving deep with us today.